Hello students, yesterday we have calculated the velocities after collision in elastic collision in one dimension. So in that the formula we have derived for the velocity of body A, that is v1 equal to m1 minus m2 upon m1 plus m2 u1 minus 2m2 upon m1 plus m2 u2. So here we have done means we have put here the negative sign, but it will be not negative, it will be positive. The calculation we have done here, just check once. This is m2 v2 minus u2 and m1 u1 minus v1. So we'll see here, this is m2. In place of v2 we are putting here the value, that is u1 plus v1 minus u2. So it is u1 plus v1 minus u2 and equal to m1 u1 minus v1. So this is m1 u1 and m2 u1 and m2 multiplied by v1, that is m2 v1 minus, you will see here u2 and u2 will be add up and this will become minus 2 m2 u2 equal to m1 u1 minus m1 v1. m1 v1, this negative sign is here, will take this side, so it will become positive and it will be m2, this is m2 v1, and from here we have taken m1 v1. Now we'll transfer this m2 u1 that side, so it is positive, it will become negative m2 u1, and this minus 2 m2 u2, this is minus here, and we have done wrong calculation that we are just transferring this side, so this minus will become plus, but by mistake we have written it minus only. So the minus will become plus here, and this is also plus, so this value also will plus. So actually the formula for the velocity v1 will come m1 minus m2 upon m1 plus m2 u1 plus 2m2 upon m1 plus m2 u2. Now the formula for v2 also we have derived already, and this formula is 2m1 upon m1 plus m2 minus m1 minus m2 upon m1 plus m2 u2 it is. Okay, so here also you will see this is this 2, the formula for the velocity of the body B. Okay, now we'll see some special case, that is case 1 here, when mass of two bodies are equal, that is m1 equal to m2, say m it is. Okay, so the formula which we have derived for the velocity of body A after collision is v1 equal to m1 minus m2 upon m1 plus m2 u1 plus 2m2 upon m1 plus m2 u2. Now we'll put the value in place of m1 m2 as m. So this will become m here, this is also become m, and it will come v1 equal to m minus m upon m plus m u1 minus, in place of m2 m, this is also m plus m, so 2m upon m plus m u2 here. So what we'll find, m minus m will be 0, so the first term will become 0 here, and the second term will be, this second term will be 2m upon 2m, so the second term will come 2m upon 2m u2. That means the v1 will be equal to u2. Okay, now we'll check for the v2. v2, the equation is given here, that is 2m1 in place of m1, I am just writing here, that is v2, you will see minus m1 minus m2 upon m1 plus m2, this is u2. Okay, so in place of m1 this is m only, this is also m plus m will come 2m, it is u1 minus m plus m, so the second term will become 0 here, so second term will become 0 and this will be 2m will be cancelled, so it is coming u1. So what we observe here, in when the two bodies are equal in mass, so their velocities after collision will change. That means before collation the velocity of body B will become after collation the velocity of body A, and the velocity of body A will become the velocity of body B. That means you will find that here the change will be means total the velocity will be interchange, and so what we conclude, when two bodies of equal masses undergo perfectly elastic collation in one dimension, their velocities are just interchanged, and these are having this phenomena is having great application. This result has an important application in a nuclear reactor, that fast moving neutrons in a nuclear reactor are slowed down by making them collide against the nuclei of moderator. Moderator moderator contain actually the hydrogen atoms or the proton, you can say, that is heavy water or the paraffin, which is somehow equivalent to the mass of the neutron. So in that case both are having almost equal masses, so the total energy of the neutron can be changed here. And what happen in that case, the nuclei of a moderator, that is hydrogen atom or that is proton, have roughly the same mass as that of neutron on a collision. So fast moving neutron are slowed down, transferring their energy to protons, and therefore hydrogenic material like heavy water or the paraffin etc. are the base suited moderator in the nuclear reactors. Case 2. When the target body B is initially at rest, that is U2 is equal to 0. So the velocity of body A after collision will be equal to m1 minus m2 upon m1 plus m2 u1. Second term containing u2, since u2 is 0, so second term will be 0. So v1 will be equal to this. Now the v2, that is the velocity of body B after collision, will be equal to 2m1 u1 upon m1 plus m2, and the second term will be 0 which contain u2, so v2 will be 2m1 u1 upon m1 plus m2. Now in this case, if we'll apply the previous case, like the mass of the two bodies equal, that is m1 equal to m2 equal to m, in such case from this formula v1, the velocity v1, so this m minus m it would be, and m1 m plus m it is u1, that means it will be 0, and v2 will be equal to, this is equal to 2m u1 upon m plus m is 2m, so 2m will be cancelled, and this is u1. So here also you will see that the velocity will interchange, that means the velocity of body A will be equal to the velocity of body B after collision. That means you will find here v1 is equal to 0, which was u2 before, that means the second body's velocity is 0, and you will find second body velocity will be 0 before collision, so after collision the first body velocity will become 0 here, and the second body velocity will become u1 after collision, which was the velocity of the first body. That means the velocity of the two bodies will interchange, and we can say simply the body A comes to rest and body B starts moving with the initial velocity of A, and obviously in such a collision 100% kinetic energy of A is transferred to the body B. Case 3. When target body B at rest is very heavy, that means m2 is very large in comparison to m1, and u2 is equal to 0. So in that situation we can write here the formula for velocity of body A is v1, which is equal to m1 minus m2 upon m1 plus m2, and the second term is 0 there, so that is u2 is 0, so second term would be 0 here. And because m2 is much greater than m1, that means we can neglect m1 here. So what we can write v1 is equal to, in m1 will be neglected, so this is m2 upon, this is upon m2, and it is u1. So it is what, m2 would be cancelled, and we can say v1 is equal to minus u1. That means the body A will acquire the same velocity as it was before collision, but the direction will be changed. Okay, now we'll see in case of velocity of body B. So you will find here this is v2 and it is equal to 2m1. This is equal to 2m1, m1 plus m2 u1. Second term would be 0 here, so second term u2 is 0, so second term would be 0, and v2 is equal to 2m1 upon m1 plus m2 u1 here. So what you will find, once again we will neglect the quantity m1, so we will say that v2 is equal to, here you will find this will be what, m1, this is m1 and m1 is very small comparison to m2, so this can be changed here, and we'll say the v2, the whole m1 can be 0, means tends to 0 you can say. So in such case you will find this term will be 0, so whole term will be 0 here. Okay, so what we can say, the velocity of body B will become 0. Hence, when a light projectile body A collide against a heavy target body B at rest, a rebound with its own velocity and B continues to be at rest. We have already calculated v1 is equal to minus u1, that means the body. So v2, that is the body B, the velocity of body B after collision will become 0, and the velocity of body A after collision will be same that it was previous, but the direction will change. So what we find here, when a light projectile body A collides against a heavy target body B at rest, a rebound with its own velocity and B continues to be at rest. And this is what happened when a ball rebound to the same height from which it was thrown on striking a floor. Next we'll see case 4. In case 4 we can see here that when target body B is at rest and has negligible mass, that means what we are considering here, that is, first of all u2 is 0 because the target body B is at rest, and mass is negligible, that means m2 is very less than m1, or simply you can say you can keep m2 as 0 also. Okay, so in that situation we have already derived the formula for the velocity of body A after collision. This is m1 minus m2 upon m1 plus m2 u1. So here we are just neglecting m2, so v1 will become, this is m1, and upon m1 u1 u1, that means m1 would be cancelled and v1 will be equal to u1. That means the velocity of body A after collision will be same as the velocity of body A before collision, and means it will continue in the same, it will continue in the motion with the same velocity in the same direction, the body A. Okay, now we are talking about the body B, V2, that is equal to, you will find here the V2 is equal to 2m1, m1 plus m2, and this is u1. So here you will see that already we have said the m2 is very less than m1. That means we can neglect m2 here. So this is 2m1 upon m1 u1, and m1 would be cancelled. So v2 will be equal to 2u1. That means the body B, which is the targeted body, will continue in motion but with the double velocity of the body A, with the double velocity of the body A. Hence what we find here, we'll just find that when a heavy projectile body A undergoes an elastic collision with the light target body B at rest, the body A keeps on moving with the same velocity of its own, that is of its own, that means v1 equal to u1 here, and the body B starts moving with the double the initial velocity of A. So a head-on elastic collision between two balls moving in opposite direction, that is this can be the example of this case. Perfectly inelastic collision in one dimension. It is explained in the figure, the the body A of mass m1 moving with the velocity u1, another body B of mass m2 initially at rest. After collision, m1 and m2 are moving with the same velocity v, as it is stated in the perfectly inelastic collision. The relative velocity of separation between the two bodies after collision is 0. That means v1 equal to v2 equal to v. So both the velocity will stick together and will move together with the same velocity v. Okay, both the bodies will stick together and move with the same velocity v here. So here we refer to this body, the first body as the projectile and the second body as the target here. So after the collision, the two bodies are moving together with the common velocity v. So we are going to calculate now this common velocity by the formula. Just apply here the total linear momentum before collision is equal to the total linear momentum after collision. So in perfectly inelastic collision also, we are taking here the total linear momentum before collision is equal to the total linear momentum after collision. So before collision, the linear momentum is m1 u1 plus here m2 u2, and after collision it will be m1 plus m2, and the common velocity v is here. So we can write v is equal to m1, this is m1 u1 plus m2 u2 upon m1 plus m2. This will be here, but as already we have state there the u2, that the target body is at rest, so u2 will be 0, and so the formula will become v, and that is equal to, this is equal to m1 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 upon m1 plus m2, and it is equal to u1. So this will be the formula for the velocities of the two bodies after collation, and you know very well, because you will find that m1 is, this m1 is obviously less than m1 plus m2. So what we can say, this fraction m1 upon m1 plus m2 is less than 1, and because it is less than 1, so obviously this velocity v will be, that means the final velocity of the two bodies v will be less than the initial velocity of the first body or the projectile body before collision. Okay, and in case of perfectly inelastic collision, already we have seen the linear momentum is conserved, so that we have put the formula, the linear momentum before collision is equal to linear momentum after collision. But we know that there is some loss in the kinetic energy in the form of heat or the sound. So here we are now going to calculate the loss of kinetic energy in this collision. So the loss of kinetic energy, to prove this there is loss of kinetic energy, what we'll do, we'll just take the kinetic energy before collision and kinetic energy after collision. So we'll find here, first of all, the kinetic energy before collision, that is E1, and this is half m1 u1 square, and since u2 is 0, so the second term will be 0, only half m1 u1 square will be there, and the kinetic energy after collision, so it is equal to E2, this is equal to E2, and it is half m1 v square plus half m2 v square. So I am taking here half as a common factor, and this is m1 plus m2, and it is v square. Now if we'll just take this value, that is the loss of kinetic energy will be there, the loss of kinetic energy will be there if E1 minus E2 will come positive. The E1 minus E2 will come positive, that means E1 will be greater than E2, that means initial kinetic energy or kinetic energy before collision will be more than the kinetic energy after collision. Then it will be proof that there is loss of kinetic energy. So to prove that, we are proving here this quantity E1 minus E2 is positive. So we'll just put the value here of E1 and E2. E1, the value is given half m1 u1 square, and E2 value is given half m1 plus m2 and v square. So we can take half common here, and you will find this is m1 u1 square minus m1 plus m2, and in place of v we'll just put the formula which we have derived for v. This is m1 upon m1 plus m2 u1 here. So we are going to calculate now the formula, that is m1 upon m1 plus m2, this is whole square, and u1 square. So it is half m1 u1 square. You will find that m1 plus m2, here this will be cancelled and this also will be cancelled, that is m1 plus m2 here. Okay, so because it is a squaring, so one term will be cancelled only, so another term will remain, that is here m1 square. Look at here, m1 square, and at upon it will be m1 plus m2, and this is u1 square. Okay, now we'll find half. Just multiply m1 u1 square with this denominator, so we are taking LCM here. This is m1 plus m2, so this term will be multiplied with m1 first. It will become m1 square u1 square, plus it will become plus m1 m2 u1 square, minus this is m1 square u1 square. So we can say here this is m1 u1 square and this is also m1 square u1 square. So these two term will be cancel out each other and it will become half. Remaining here is the m1 m2 upon m1 plus m2 u1 square. Okay, so we are just writing this as a del k. Del k, that means it is the difference of the kinetic energy before collation and the kinetic energy after collation. So what you will find here, this quantity m1 and m2 are positive, so this quantity will be positive. If u1 is negative, then also the squaring of the negative will become positive. So what you will find, the value at the right hand side will be positive. Obviously the value at the left hand side also will be positive. That means simply we can say the del k is a positive value. Del k is the positive value, that means the E1 is E1 minus E2 will be a positive value. This E1 minus E2 will be a positive value, and it will be positive value means E1 is greater than E2. E1 is greater than E2. That means the kinetic energy before collation will be more than the kinetic energy after collation. So it is proven now that the loss of kinetic energy will take place in case of perfectly inelastic collation in one dimension. Elastic collation in two dimension. If the initial velocities and final velocities of both the bodies are along the same straight line, then it is called a one-dimensional collation or head-on collation. In the case of a small spherical body, this is possible if the direction of travel of the body 1 passes through the center of the body 2. So in general, the collation are two dimension, where the initial velocities and the final velocities may lie in a plane. So when two bodies traveling initially along the same straight line collide without loss of kinetic energy and move along different direction in a pair in a plane, so after collation, the collation is said to be elastic collation in two dimension. Here we are taking the two body A and B. Now suppose m1 m2 are the masses of two bodies A and B moving initially along x-axis with velocity u1 and u2 respectively, and when you will find that when u1 is greater than u2, so somewhere somewhere the body A will collide to the body B, so the two bodies collide, and after collision let the body A move with the velocity v. You can see the direction velocity v at angle theta just making angle theta with the x-axis, and let the body B move with the velocity v2 at an angle phi with the x-axis as shown in the figure here. Okay, so we'll see here the theta is known as the angle of scattering and phi is known as the angle of recoil. As the collision is elastic, so the kinetic energy will be conserved, and that means what we can say, the total kinetic energy, because it is a perfectly elastic collision, so the total kinetic energy must be conserved, and it is before collision will be equal to after collision. So total kinetic energy after collision will be equal to kinetic energy before collision. Kinetic energy is scalar quantity, so here the addition will be as the scalar quantity, that is m1 v1 square plus half m2 v2 square, and this is half m1 u1 square plus half m2 u2 square, or simply we can say, when we simplified it, m1 v1 square plus m2 v2 square must be equal to m1 u1 square plus m2 u2 square. Okay, now since it is the elastic collision, so linear momentum also will be conserved, but linear momentum is a vector quantity, so we'll take this as a vector form. Like first we'll take along x-axis the linear momentum before collision will be equal to after collision. So you will see that along x-axis you will find before collision it is m1 u1 plus m2 u2, and after collision if you just take in the x-axis you will find the velocity of the body A is v1. So you can resolve this into two components. The horizontal component is v1 cos theta and the vertical component is v1 sin theta. Here you will find for the body B, that is it is moving with the velocity v2, so that can be also resolved in two component. In this direction it is v2 cos phi, and in this direction this will be v2 sin phi. Okay, so along x-axis what we have observed, the momentum, that is equal to m1 v1 cos theta plus it is m2 v2 cos phi. Okay, so this is our equation 1, this is our equation 2, and if we just check along y-axis, we'll check along y-axis the linear momentum, that is pi is equal to pf, the initial linear momentum, or you can say the linear momentum before collision is equal to linear momentum after collision. So what you will find, initially there is no linear momentum in the y direction because both the bodies are moving in the x direction only, so no linear momentum is there. That means pi must be equal to 0, and pf you will find can be in the vertical upward direction or maybe in the vertical downward direction. It depends on the value of v1 sin theta and v2 sin phi. So we can write here that pf, that the final momentum will be along y-axis will be m1 v1 sin theta minus m2 v2 sin theta. Surely it will be, sorry, sin phi. Surely it will be a difference of these two, but whichever will be greater in that direction, the resultant will be obtained. So you will find this is equation number 3. Now the interesting thing is that we have four unknown values, that is v1, v2, theta and phi, and we have three equations only. So whenever we have to solve any of the unknown quantity, that many equations will required. If four unknown quantities are there, so we will require the at least four equations. Okay, so that means if we are going to calculate v1, v2, theta and phi, so any one value may be given, so rest three value we can calculate by this formula. We'll see the special case in case of elastic collision in two dimension. So the special case is suppose the initial velocity of body A is taken as u and body B, that is u2, is equal to 0, and the masses of the two bodies, that is m1 equal to m2 equal to m. That means when two particles of same mass undergo perfectly elastic collision in two dimension. So we are looking here in which the second body is at rest initially. So the formula you can see previously, which we have calculated the equation 1, that is m1 v1 square m2 v2 square. So from this equation only I am just writing m1 v1 square m2 v2 square and equal to m1 u1 plus m2 u2 square. Okay, now we'll just put the value here. When we are putting the value, u2 will be equal to 0, so it will come, this will be mass are same, so it is m v1 square plus m v2 square equal to m u square. This term will be 0 since u2 will be 0. M we can take common and that can be cancelled out, so it will become v1 plus v2 square equal to u square. I am writing this as equation 4 here. Okay, now from equation 2 you will see that equation 2, this is m1 u1 plus m2 u2 and equal to m1 v1 cos theta plus m2 v2 cos phi. So here I can just put the value, that is m1 and m2 as m, so this is m and this is m. u1 will be there but the second term will be 0, so it will be m u. This will be equal to m u, and you will find here this is m v cos theta, m v cos theta, and this is m v cos phi. Okay, m v1 cos theta plus m v2 cos phi. So we'll write this as, look at here, this is as v1 will write m u, this is equal to m v1 cos theta plus m v2 cos phi. We can take m common and that can be cancelled out, so v1 cos theta plus v2 cos phi is equal to u, and this is our equation 5th. Okay, now from equation 3 we will see here, this is equation 3, this is, so you will find 0 m1 v1 sin theta and minus m2 v2 sin phi. In place of m1 I am just writing m, and here also m, so simply that v1 sin theta will become v2 sin phi. So the equation we'll obtain is v1 sin theta minus v2 sin phi equal to 0, or we can say v1 sin theta is equal to v2 sin phi, and this we got from equation 3. from equation 3 we got this relation. Okay, so this is equation 3 and this I am writing as equation 6 now. So what we can see from equation 4, the equation 4 which we have derived, so from equation 4 which is v1 square plus v2 square equal to u square, and from equation in this only we'll just write the value of v1 and v2 here. So we can write the v1 v1 square plus v2 square, and this is u. The u is given by equation 5 and it is equal to v1 cos theta plus v2 cos phi. So it is v1 cos theta plus v2 cos phi. Okay, this will be equal to, because squaring is there, so this is whole square. Now you will see that v1 square plus v2 square is equal to, this is v1 square cos square theta plus v2 square cos square phi plus 2v1 v2 cos theta and cos phi it would be. Okay, now we'll see here, this is if we transfer v1 cos square theta this side and v2 cos square theta this side, so it will come, v1 square will take common, it is 1 minus cos square theta and plus v2 square is 1 minus, v2 square in the bracket 1 minus cos phi here. Okay, and this is 2v1 v2 cos theta cos phi. Now v1 square 1 minus cos square theta we can write as sin square theta, and here v2 square, this also we can write as sin square phi. Okay, so this is sin square phi and this is 2v1 v2 cos theta cos phi. Now we'll see here the v1 sin theta from equation 6th. You can see the v1 sin theta equal to v2 sin phi. So we can write any of the equation, whether we can replace v1 sin theta as v2 sin phi or v2 sin phi as v1 sin theta. So I'm just writing here, this is v1 square sin square theta, and since it is v2 square cos square phi, this as this also as the v1 square sin square theta, and this is 2v1 v2 cos theta cos phi. So what you will find here, this will be 2v1 square sin square theta and 2v1 v2 cos theta cos phi. Okay, now we'll see here the cos theta, the value of cos theta we can write here, this is 2v1 square sin square theta upon, this is 2, we'll find this is 2v1 v2 cos phi. 2 would be cancelled, v1 would be cancelled, it will come cos theta is equal to, this is v1 sin square theta upon, here it is v2 cos phi, v2 cos phi, but this I'm just writing as equation 7 first. Okay, so we know that by the formula cos theta plus phi, cos A plus B is equal to cos A cos B minus sin A sin B. So here we will write cos theta cos phi minus sin theta sin phi, sin theta sin phi. So we can just put this equation here, that is cos theta plus phi. You will see in place of cos theta, here it is cos theta, we'll just put the equation, this 7th equation. So it is v1 sin square theta upon v2 cos phi in place of cos theta, and this is cos phi already, it is here cos phi, minus this is sin theta. This is what? This is v1. v1 will just multiply here, so you will find this is also the cos theta value will be there. So this is v1 in place of sin theta from this equation, sixth equation. Look at here, from this sixth equation, in place of sin phi we can write v1 upon v2 sin theta. Okay, v1 upon v2 sin theta in place of sin phi. So here also I am just writing v1 upon v2 sin theta. Now you will get cos theta plus phi is equal to cos phi will be cancelled. It is v1 upon v2 sin square theta, and minus this is also you will get here because sin phi is there, so we'll get v1 upon v2, sorry, sin theta into sin theta, that is sin square theta, and both the values are equal, so it will come 0. That means we are getting here cos theta plus phi equal to 0, and cos theta plus phi equal to 0, so obviously that theta plus phi must be 90 degree. So we will conclude here that in a perfectly elastic collision in two dimension between two particles of same mass, the two particles move along mutually perpendicular direction after the collision.